Welcome to the Deep Dive, where we peel back the layers on the everyday to unearth the incredible stories hiding in plain sight.
It's always fascinating what you find when you look closely.
Exactly. And today, we're zeroing in on an object so common, so completely taken for granted, you probably have dozens of them holding your world together right now.
Yeah.
We're talking about that small, sharp warrior of construction, the humble nail.
The nail. Seems so simple, doesn't it?
Totally. Yet this seemingly mundane piece of metal, often overlooked, holds a rich history and tells a surprising, monumental story of incredible technological evolution, human ingenuity, and the very fabric of how we've shaped our world over millennia.
It really does. Its story is, in many ways, the story of building itself.
So we're embarking on a deep dive into the hidden world of these fundamental construction elements. While these components might seem simple, even primitive, as we'll uncover, they are profoundly intertwined with major shifts in human innovation, industrial progress, and the fundamental way we design and erect our built environment.
The connections are deeper than most people probably realize.
Our mission today is to truly unpack the story of this specific type of fastener, what the articles, research, and notes you've shared reveal about its journey, from ancient techniques in the earliest forges to modern construction practices.
Yeah, looking at everything from the materials, the methods.
And the massive, often unseen impact of these small but mighty components. Okay, let's unpack this. How something so small can tell such a colossal story, a story that truly defines our ability to build.
What's truly fascinating here is how the materials and techniques, even for something as seemingly basic as a nail or, the methods that predated it, illuminate broader historical and technological landscapes.
Right.
The evolution of how we've chosen to put things together, even at this micro level, it sort of mirrors the macro changes in human society, from the engineering marvels of ancient empires right up to the precision of the digital age.
It really is a testament to continuous human problem solving, isn't it?
Absolutely. Constant adaptation and innovation.
So let's cast our minds way, way back to a time before nails as we know them were common, or maybe even existed in their modern mass-produced form.
Yeah, long before you could just buy a box of them at the hardware store.
Right. Despite this, complex fastening methods were absolutely essential for building the great structures of the ancient world. It really makes you wonder how they managed without the ubiquitous metal fasteners we rely on today. How did they achieve such incredible feats of engineering?
It's a crucial question because we often operate under this assumption, right, that advanced construction inherently requires advanced metal fasteners. But ancient builders, particularly in civilizations like Rome, possessed incredibly sophisticated alternatives.
Alternatives. Like what, for instance?
Well, to illustrate this, let's dive into an intriguing detail from Andrea Palladio's seminal work, The Four Books of Architecture, concerning a truly remarkable structure, the Pons Sublicius.
The Pons Sublicius. Okay, refresh my memory on this one.
This wasn't just any bridge. It was an ancient and critically a perpetually serving wooden bridge over the Tiber in Rome, reputedly built by King Ancus Marcius.
Wow, okay, so we're talking really early Rome.
Exactly. For context, this was Rome's very first bridge, a strategic lifeline dating back to maybe the 7th century BC. Its longevity and importance alone make its construction fascinating.
Definitely.
Indeed. And what's truly remarkable about this bridge, according to Palladio, writing much later, of course, but recounting its tradition, is its unique construction. Its beams were joined together with so much art that one could take them away and replace them according as necessity should require.
Joined together with so much art. That phrasing is interesting. Modular, almost.
Kind of like ancient Lego, maybe? But here's the crucial detail, the part that truly stands out and challenges our modern assumptions. Palladio explicitly states there being neither nails nor any iron whatsoever in it.
No iron at all in a major Roman bridge.
None. 0 iron fasteners, according to the tradition Palladio recorded.
For a critical, perpetually serving bridge in ancient Rome, a structure that was essentially the gateway to the city from the south. That detail is absolutely striking. It forces us to ask, what does that truly signify about their engineering priorities and, well, the very fabric of their society?
Yeah.
Is it simply a testament to their resourcefulness, or perhaps a deliberate design philosophy we often overlook?
He challenges our modern metal-centric view of construction, doesn't it? The absence of iron isn't just a fun historical fact. It's a profound window into an era where metal, particularly refined iron, was immensely valuable.
Okay, so value is key here. Iron wasn't cheap or easy to come by.
Not at all. While we don't have sources directly stating Roman nails were used as currency for this specific bridge context, the general implication of iron's high value is clear throughout antiquity. Obtaining the ore, smelting it, forging it, it was an incredibly laborious and expensive process.
But using it unnecessarily like in a huge bridge would have been extravagant.
A massive investment of scarce resources, certainly. So the choice to avoid iron in the Pons Sublicius was likely multi-layered. Firstly, it implies an immense mastery of sophisticated wooden joinery techniques.
Right, they must have been incredible carpenters.
Oh, absolutely. We're talking intricate mortise and tenon joints, precisely cut wooden pegs, dowels, wedges, maybe even complex scarf joints, and carefully angled beams designed to hold under immense tension and compression without a single metal fastener.
Wow.
These weren't crude connections, they were highly engineered, often relying on the wood's natural property, its grain, its strength, its response to moisture, and the forces of gravity to lock components together securely.
So it wasn't necessarily a limitation then, more like a deliberate design choice, favoring flexibility and perhaps ease of repair over the rigid permanence that iron fasteners might offer.
That's a very strong possibility. Think about it. You mentioned defense earlier. I can see how a modular bridge that could be quickly dismantled would be a huge strategic advantage in times of conflict.
Yeah, love the drawbridge, Roman style.
Sort of. Or, prevent an enemy from using your own bridge against you. It speaks volumes about their woodworking and engineering prowess, a different kind of sophistication than we typically imagine.
It really does. It shifts the perspective.
Absolutely. The ability to easily disassemble and reassemble parts was vital. Think of it as ancient modular construction, as you said. If a section was damaged by flood or battle, or if they needed to prevent an enemy crossing, it could potentially be rapidly taken apart.
Makes sense.
This suggests a very pragmatic approach to engineering, where function, maintainability, and strategic flexibility dictated material choice, rather than simply going for the most advanced material available at the time.
So they weren't just throwing iron at every problem.
No, they leveraged the inherent properties of wood to create durable and adaptable structures, demonstrating an ingenuity that modern construction, sometimes overly reliant on standardized metal parts, can maybe overlook. The art Palladio speaks of isn't just aesthetic, it's the art of understanding materials deeply.
That's a powerful point about prioritizing flexibility and resourcefulness. It makes me wonder, given their mastery of different materials, was the choice to avoid iron in the Pons Sublicius an isolated incident? Or do we see echoes of this material pragmatism in other aspects of Roman construction?
Good question.
They certainly knew how to make things last, even with different material strategies, like their concrete, for instance.
You're right to ask that. They were far from ignorant of other sophisticated construction materials and methods. As a contrast, we can look to other Roman construction techniques, drawing from Vitruvius's The 10 Books on Architecture, another cornerstone text on ancient engineering.
Vitruvius, right, the authority. What does he say?
He describes, for example, how to construct walls of smallest stones, rubble masonry, essentially thoroughly puddled with the mortar, which is made of lime and sand, to hold together longer.
Thoroughly puddled. That phrase alone conjures an image of careful, deliberate mixing, almost like making a perfect dough or something.
Kind of, yeah. But what was so critical about this specific mortar, and how does it relate to the absence of metal fasteners in other structures?
Okay, tell me more.
The emphasis here is on the absolute critical importance of mortar's moisture content for achieving its full strength. Vitruvius understood that if those thirsty, porous stones absorbed the moisture from the freshly mixed mortar too rapidly—
Before the chemical reaction could happen.
Exactly. Faster than the lime could undergo its critical chemical reaction known as carbonation, the mortar wouldn't properly cure. It would simply dry out, becoming brittle and crumbly, almost like hardened dust, rather than forming a strong, cohesive binder.
So the wall would basically just fall apart.
Pretty much. Imagine trying to build a solid wall with sand glued together with dried mud. It would crumble at the slightest stress. This wasn't just a technical detail for Vitruvius, it was a fundamental understanding of material science that determined whether a Roman wall stood for centuries or collapsed within a few seasons.
Incredible foresight.
So if we connect this to the bigger picture, the Roman reliance on advanced mortar in stone structures shows a parallel sophistication in material science, even without metal fasteners. It raises that important question again. Was the absence of iron in the Pons Sublicius a limitation? or a deliberate, masterful design choice.
Right. It seems they knew exactly what they were doing with all their materials.
It points to a deep understanding of all available materials and how to optimize their use for specific functions. Their ingenuity wasn't confined to metalworking. It spanned the entire spectrum of available resources. They used what worked best for the job, whether it was wood, stone, or their amazing pozzolanic concrete.
So we've seen how the Romans deftly avoided iron in certain critical structures, maybe out of choice, maybe out of economic necessity, maybe both.
Mm-hmm.
But that doesn't mean the ancient world was ignorant of metallurgy. In fact, the foundational knowledge for working with metals, the very bedrock upon which future fasteners would eventually be forged, was being painstakingly accumulated over centuries.
A slow, cumulative process.
Exactly. To truly appreciate this long, arduous journey of discovery, we can fast forward, chronologically, to a pivotal work that synthesizes this accumulated wisdom. George Agricola's De Re Metallica, published in 1556.
Agricola's work, yes. While it's centuries after ancient Rome, it's a monumental treatise on mining, smelting, and metallurgy, reflecting centuries of accumulated empirical knowledge and practice passed down through generations of craftspeople.
So it's like a snapshot of everything they'd learned up to that point.
Pretty much. It shows us the deep foundational understanding of metals that was slowly but surely building up, knowledge that would eventually underpin the creation of all metal components, including effective fasteners like nails.
And when you describe those minute details in Agricola, the gradual heating, the assaying, the bellows, it paints such a vivid picture of meticulous, almost alchemical effort. I can only begin to imagine the sheer human labor and the highly specialized, maybe even secret, knowledge required just to get these raw metals.
Oh, absolutely. It sounds like an entire hidden industry, doesn't it? Agricola describes, for instance, how to assay an alloy of copper and silver. He details the process.
How does he describe it?
Imagine the metallurgist carefully slicing small to large samples from a large slab or cake of copper, perhaps a rough ingot just pulled from an earlier smelting. These small pieces are then cradled in a triangular crucible, a specialized ceramic vessel designed to withstand intense heat,
Okay.
and gradually heated over a fire. It's not a quick blast, it's a patient dance, slowly raising the temperature until the copper glows a deep, fiery red, indicating it's ready for the next critical stage of purification.
Wow. Patience was key.
Definitely. And the details don't stop there. He talks about stimulating the fire with a blast from double bellows for half an hour to melt the copper completely.
Double bellows, even.
Right. And if it doesn't stir easily, it means it's not wholly liquefied, and more charcoal and blowing are needed. This isn't just a simple description. It's an instruction manual born from generations of trial and error.
So much observation involved.
Exactly. The use of double bellows wasn't just to make the copper stir easily, but to achieve a specific controlled intensity of heat, the difference between a sluggish, half-melted slag and a truly refined liquid metal. This wasn't guesswork. It was a deeply empirical, hands-on science developed over generations, a true testament to early material engineering.
Amazing.
He also goes into remarkable detail about refining copper from sulfide ores, which was a significant advancement, and even the recovery of zinc oxides from furnace fumes, which indirectly, according to Dioscorides much earlier, provided the first definite indication of how to make brass.
So they were figuring out alloys, too.
And it wasn't just about copper. Agricola also details processes like separating lead from silver through liquation.
Liquation, what's that?
It's where a silver-lead alloy is heated, and the lead, having a lower melting point, literally drips or liquates through porous copper plates, leaving the more refractory silver behind. And he meticulously lists the tools involved. Iron hoops to bind furnaces, tongs for handling molten metal, sieves made of street and cross iron wires, bronze ladles for pouring, and molds for casting the refined silver-lead cakes. The level of detail is just incredible.
It really sounds like it. Here's where it gets really interesting. Imagine the sheer effort and specialized knowledge behind just getting the raw materials for any metal component back then.
This extensive hands-on knowledge of working with and refining various metals laid the critical groundwork for the future production of all kinds of metal components, including fasteners.
Right, the foundation.
The ability to manipulate these materials, to understand their properties, to extract and purify them was painstakingly developed over centuries. This accumulated knowledge wasn't just theoretical, it was the slow, arduous, and sometimes dangerous path that would eventually lead us away from pure wooden joinery and towards the widespread adoption of metal components, including our humble nail.
A centuries-long apprenticeship in bending the Earth's elements to human will, as you put it.
Precisely.
And as we move from that foundational, painstakingly gathered understanding of metals into the pre-industrial era, say the 17th century, we begin to see these burgeoning metalworking skills translate into more explicit and intricate applications of fasteners in everyday craft and early manufacturing.
Yeah, things start to get a bit more specific, a bit more documented in terms of usage.
We start to see not just the ability to make metal components, but the deliberate choice to integrate them into complex machines and structures. This is where we glimpse the early life of our subject, the iron pin and the nascent nail.
That's precisely right. Let's open a window into the 17th century craft world with Joseph Moxon's Mechanic Exercises, published around 1678. This text is invaluable because it doesn't just describe what was built, but how it was built, piece by careful piece.
A real hands-on guide.
Exactly. Moxon provides a detailed account of constructing a printing press, which is an excellent, sophisticated example of complex machinery reliant on individual, meticulously crafted fasteners.
Okay, a printing press. Complex indeed. What kind of fasteners does he mention?
And the detail here is fascinating. He specifically describes iron pins used to join integral parts of the press. For instance, he writes about parts being pined into the feet with an iron pin, or how another iron pin is used to pin the tenant into the cap.
So specific iron pins, not just wood.
Right, the material is highlighted. These aren't just vague references, they're precise instructions for assembly. What's more, he explicitly mentions, nailed down on the upper side of the plank, 2 female dovetail grooves.
Ah, nailed down. So nails are explicitly appearing alongside these pins.
Yes, they are. This is significant. These are not just decorative elements. These are precise connections vital for the functional operation and structural integrity of a complex machine like a printing press. It shows how critical these individual metal fasteners were for both structural integrity and accurate assembly in a craft setting.
It signifies a stage where metal fasteners were specific, deliberate choices, maybe custom-made or at least carefully selected for their role.
I think that's fair to say, and it makes you think about the labor involved. You mentioned earlier the focus for this episode, about colonial-era nail-making being a laborious but essential household task. While Moxon's context is 17th century England, not colonial America, the spirit of painstaking hands-on craftsmanship for these fasteners clearly resonates.
Absolutely. It wasn't automated, that's for sure.
Not even close. This raises an important question. How much of the skill and labor, which we associate with the craft tasks of that era, was hidden in the production and meticulous application of these seemingly simple pins and nails?
Good point. We see the finished product, not the hours spent making the parts.
Exactly. The descriptions in Moxon imply a highly hands-on, often individual approach to both producing or acquiring and using fasteners in the pre-industrial era. It wasn't about mass production as we know it today, but about skilled craftsmanship. Each pin, each nail would have been a product of considerable effort and expense, whether made by a local blacksmith or perhaps even forged on-site for larger projects.
So the term iron pin, rather than just pin, likely indicates the value and specific material choice, highlighting its importance over a wooden alternative, right?
That seems very likely, yes. Iron was still a valuable commodity.
And this wasn't just for specialized machinery like printing presses, presumably. If we connect this to broader descriptions of general construction like timbering and lath and plaster mentioned in sources like The Pattern of English Building or Building Construction Illustrated, we can infer that such painstakingly crafted fasteners would have been crucial across a wide range of common building practices too.
Absolutely. The Pattern of English Building mentions timbering as a fundamental construction practice, which, by necessity, would have involved a great many joints requiring fastening, whether purely wood on wood or supplemented with metal.
Right.
And lath and plaster is described as a traditional 2-coat gypsum plaster applied to lath, often supported by wood or metal stud framing, though metal studs are much later. The lath itself, thin strips of wood, had to be nailed to the framing.
So lots of small fasteners needed there.
Tons of them. While the sources we're looking at don't explicitly detail the making of nails as a household task in the same way maybe some colonial American accounts do, the presence and specific application of these metal fasteners in Moxon's work and the general construction descriptions certainly imply a time-consuming, skilled process of either acquiring or crafting them.
Imagine the sheer time and effort required to produce and install every single one in a new home or building.
Consider the implications. A single nail was a resource. It represented labor, the mining of ore, the smelting, the forging, the shaping by hand, often one by a blacksmith or nailer.
Right. It wasn't trivial.
So every time a carpenter struck a nail, they weren't just joining two pieces of wood, they were expending a measurable amount of embodied labor and material value. This likely drove efficiency in their use, demanding precision in every hammer blow because each fastener was precious, especially compared to today.
Makes sense. You wouldn't waste them.
This level of intrinsic value probably meant that even in general construction, nails and pins were used judiciously, complementing elaborate wooden joinery rather than entirely replacing it as they might today. It was a far cry from the modern practice of rapid-fire nailing with a pneumatic gun.
A completely different mindset about materials and labor.
Which brings us neatly to a pivotal shift, doesn't it? A phase that drastically changed how these small but mighty components were produced and used, the industrial age.
Right. The game changes completely. We're transitioning from individually crafted or specified fasteners, often unique in their imperfections, to more standardized, readily available ones.
And this had a monumental, truly transformative impact on construction, enabling new scales and speeds of building previously unimaginable.
Suddenly, nails are everywhere.
Indeed. We begin to see nails explicitly and ubiquitously mentioned in contemporary building practices, indicating their widespread and standardized use. This marks a clear departure from the earlier era of painstaking individual craft.
Any specific examples from the text?
For example, Building Construction Illustrated details something as common today as drywall. Single-layer construction consists of 12 or 58, 13 or 16, gypsum wallboard, fastened W drywall nails or screws. The key here is the choice between nails or screws, both mass-produced.
And it's specifically noted that adhesive may be used in addition to nailing for a more secure bond, clearly identifying nails as the primary fasteners, right?
Exactly. That phrasing is telling. It shows a profound shift where nails are the default, the fundamental means of connection, and adhesives are a supplement for added security, not the main event. It speaks volumes about their newfound reliability and affordability.
They became the workhorse.
Precisely. And it's not just about their presence, but their profound standardization. Construction management and its construction support materials recap sheet lists specific sizes. Nails 8-pin and nail 6-pin.
Ah, the penny sizes. What does the D actually stand for again?
Well, the D is the old symbol for the British penny, denarius. The story goes, it originally referred to the price per 100 nails in medieval England. So an 8-penny nail was one size. A 6-pen was another smaller size.
So like 2.5 inches for an 8D, 2 inches for a 6-pen, roughly?
Roughly, yeah. The exact lengths have standardized over time. But this isn't just a random classification. It implies not only standardization in manufacturing, but also a variety of sizes designed for specific uses, framing, finishing, roofing, etc., reflecting an industrial system capable of producing precise components reliably and cheaply.
And the recap sheet takes this a step further, highlighting the economic aspect. Total quantities as well as sub-quantities identified by activity code and appropriate waste and loss factor calculations are integral to material planning for nails.
Mm-hmm.
This level of detail in project management underscores that nails are now a commodity, not a precious individual item, but a bulk material, mass-produced and integrated into highly efficient supply chains. This is a universe away from the individual iron pins of Moxon's era.
Absolutely. The ability to produce cheap, uniform nails by the ton was a direct result of pivotal innovations, especially in the late 18th and 19th centuries. That's when things really took off.
What were those key innovations?
Initially, machines were invented that could cut nails from flat iron sheets. These are the cut nails you sometimes still see, especially in historical restoration. They have a distinctive, tapered, rectangular, wedge-like shape.
Right, I think I've seen those. They look different from modern nails.
They do. Then, the even more revolutionary development, primarily in the mid to late 19th century, was machines that could form nails from steel wire.
Ah, wire nails. That sounds like what we mostly use today.
Exactly. Round, consistent, easily produced in huge quantities. This transition from hand forging to cut nails to wire nails dramatically lowered production costs and increased availability, making nails economically accessible for virtually any construction project.
And this industrialization must have also brought about significant efficiency gains in how buildings were actually put together on site.
Right. Oh, massively. Fundamentals of Residential Construction gives a good example. It details the use of steel cross-bridging for floor joists, specifically noting that it requires only one nail per piece and no cutting, so it is the fastest to install. This is a huge leap in productivity compared to traditional wooden bridging, saving both labor and time on a construction site.
So it's not just about making the nail cheaper, but designing systems around using it faster.
Precisely. Optimizing the whole process. The very idea of nail holes being mentioned elsewhere as a recognized element requiring patching and finishes rather than a critical error further indicates their widespread, common, and efficient use in modern practices. It's just an expected part of the process.
Accepted imperfection due to speed and volume.
Kinda, yeah.
Hmm.
Furthermore, Builder's Guide to Hot, Dry, and Mixed Dry Climates offers another specific, practical application, mentioning ledger nailed over top of rigid insulation as a standard method for securing structural components like deck ledgers. These small, practical mentions collectively paint a comprehensive picture of nails as indispensable, versatile, and absolutely central to modern construction techniques across a diverse range of applications, from heavy framing to delicate trim work.
So what does this all mean then? These small details about different nail sizes like 6-pence and 8-pence, the shift from cut to wire nails and how quickly they could be installed, paint a picture of a massive acceleration in how we build.
A sea change.
It feels like the unprecedented availability of standardized, affordable fasteners truly fueled a boom in wood frame construction, didn't it? It wasn't just a convenience, it was a catalyst for an entire new architectural landscape, particularly in North America.
You've hit on the core of it. This cheap, reliable nail was arguably one of the key enabling technologies for the rapid expansion of settlement and building across the continent. We see this reflected in Building Codes Illustrated, which outlines explicit provisions for conventional light frame construction in Section 2308.
Specific codes just for this type of building.
Yes, specifically designed for residential and light commercial construction. These codes detail structural limitations, things like buildings up to 3 stories in height, bearing wall stud heights limited to 10 feet, and roof trusses spanning no more than 40 feet. They also mandate requirements like braced walls for lateral loads to resist wind and seismic forces.
So the existence of these detailed codes implies this method became incredibly common, standardized, and maybe even dominant.
Absolutely. This robust regulatory framework wouldn't exist if wood frame construction wasn't an incredibly prevalent, standardized, and economically viable method. The ease and speed of using standardized nails were critical enablers for its widespread adoption and the rapid construction it allowed.
It just made building faster and cheaper.
Significantly.
Yeah.
And Fundamentals of Residential Construction also mentions upper floor framing, using remarkably similar methods as the ground floor, reinforcing this idea of standardization and the repeatability that mass-produced fasteners allowed. You could build multiple stories quickly using the same basic techniques.
Build faster, build higher, build more.
What's truly fascinating here, as you said earlier, is how the seemingly minor detail of a standardized nail, whether cut or wire, becomes a catalyst, enabling an entire new ecosystem of construction practices. We witness a profound shift from bespoke craftsmanship, where every joint might be unique, to scalable frameworks.
From art to assembly line almost.
In a way, yes. The ability to quickly and reliably join wood elements with consistent fasteners transformed construction from a craft-intensive, slow process into a more industrial, assembly line-like methodology, especially for housing. This was nothing short of a silent revolution, nail by nail, house by house, and later innovations like the pneumatic nail gun in the 20th century just amplified that speed and efficiency even further.
Right, the nail gun, another huge leap.
So it's abundantly clear that the evolution of the nail isn't just about one small object. It's a profound microcosm of a much larger story of technological and industrial change. These fasteners, or indeed their absence back in ancient Rome, serve as powerful indicators of human progress and shifting priorities throughout history.
Yeah, you can read so much into them.
To broaden the discussion, let's consider other industrial fasteners for a moment, like rivets, as a proxy for the larger, grander changes of the industrial era.
Okay, rivets, bigger scale.
We can look to Isambard Kingdom Brunel's era of grand engineering projects, such as the construction of the Great Eastern Steamship, a colossal iron vessel in the mid-19th century. The sheer scale of that project, described by L.T.C. Rolt, involved men swarming like ants about the hull, and the Isle of Dogs re-echoing the clamor of their riveting hammers.
The clamor of their riveting hammers. What an evocative image. It speaks of immense noise, intense labor, and a scale of metalworking that far surpassed what was needed for simple house nails, right?
Oh, absolutely. This kind of large-scale fastening through riveting, heating metal pins red hot and hammering them to form a head on both sides, clamping thick iron plates together was a hallmark of the burgeoning industrial age.
A totally different process.
It showed a dramatic shift from smaller, hand-driven nails and wood to heavy-duty, often machine-assisted, connections required for massive metal structures like ships, bridges, boilers, and eventually early skyscrapers. It's a different beast entirely, driven by different forces and materials, primarily iron, than steel.
And this evolution of fasteners, from wooden pegs to hand-forged nails to mass-produced nails to industrial rivets, it ties directly into fundamental architectural and engineering principles, doesn't it?
It really does. Louis H. Sullivan, the visionary architect in the Autobiography of an Idea, articulated a powerful, enduring concept, that the function of a building must predetermine and organize its form, famously summarized as form follows function.
Form follows function. Okay. So how does Sullivan's philosophy apply to our tiny, humble fasteners? It seems like such a grand concept for something so small.
But it applies directly and profoundly. Throughout history, the job of efficiently joining materials has profoundly driven the form and type of fasteners used.
Give me some examples.
Okay, think about it. From the intricate wooden joinery of the Pons Sublicius, specifically designed for disassembly and strategic flexibility, its form served that function, to the precisely fabricated iron pins in Moxon's printing press, designed for mechanical accuracy, to the mass-produced, standardized nails, both cut and wire, that enabled rapid wood frame construction, prioritizing speed and cost-effectiveness.
Okay, I see.
In each instance, the specific needs, the desired performance, and the available materials and technology dictated the fastening solutions. Each step reflected an optimization of form to serve function, driven by the technological capabilities of the time. The tapered shape of an early cut nail was optimized for holding power in wood by wedging fibers apart. The round, consistent wire nail was optimized for manufacturing speed and later for ease of use in pneumatic nail guns.
Form following function at every stage.
Exactly, and this relentless drive for efficiency and standardization continued into modernity, even beyond simple nails, influencing entire architectural movements. Think of Le Corbusier.
Ah, Le Corbusier. Modernism personified.
Right. In Towards a New Architecture, he championed standardization with almost messianic fervor. He envisioned mass production villas with framework of concrete, speaking of houses being serviceable as a typewriter, and emphasizing proportion that costs the landlord nothing.
Very industrial mindset.
Very. Even though his focus was often on concrete and prefabrication rather than timber frames and nails, the underlying principle of standardized components and industrial efficiency is directly relevant to the story we've been telling about the mass production and widespread use of nails.
It's the same impulse toward systemization.
Absolutely. Which raises an important question, doesn't it? Does standardization inherently lead to a loss of craft, or does it simply redirect ingenuity towards optimizing the system as a whole? From sourcing raw materials like iron ore or wire, to manufacturing processes, to the final installation, maybe even thinking about those nail holes in drywall.
That's a good question. Is it less craft or just different craft?
Le Corbusier's vision of efficiency and reproducibility, while aiming for different materials, reflects the same industrial mindset that made standardized nails so impactful. The focus shifts from the individual artisan meticulously crafting each component to optimizing the entire system, allowing for unprecedented speed and scale. It's arguably a new kind of craft, the craft of process optimization, of systems thinking.
And this journey of optimizing how we put things together, driven by function and material innovation, it continues even today, right? Into what's being called the third digital revolution.
It absolutely does. Texts like Designing Reality offer a glimpse into this potential future where bits will enable people to directly change the atoms, a very provocative idea.
Change the atom.
Wow.
How does that relate to building?
The vision extends to houses and cars through designs sourced globally but fabricated locally. Think 3D printing on a massive scale or other forms of digital fabrication.
So designing something anywhere, building it anywhere with automation.
Essentially. While not directly about nails in their traditional form, this concept represents the ongoing, ceaseless quest for more efficient, precise, and integrated methods of construction and assembly. The City of Tomorrow further expands on this, discussing fab labs, fabrication laboratories that might combine dwellings with fabrication, essentially homes that are also small, automated factories.
Homes that build themselves
Or
almost.
at least produce many of their own components or other goods locally and on demand. These concepts mirror the entire journey we've traced, from handworked metal pins to mass-produced nails. Each step is an attempt to achieve greater precision, efficiency, and accessibility in how we assemble our world.
It's the next logical step in that evolution.
You could see it that way. The digital fabrication model is perhaps the ultimate extension so far of standardization and industrialization, aiming to transform the physical world around us with unprecedented control and local production. It's a far cry from the limitations of ancient joinery, yet arguably driven by the same fundamental human desire to build effectively. It's a continuous, evolving narrative of how we fasten our world together.
So from ancient Roman bridges that deliberately avoided iron, relying on intricate wooden joinery, to the meticulously crafted iron pins of early printing presses, then to the mass-produced, standardized nails cut, then wire that enabled a revolution in wood frame construction, amplified by tools like the nail gun, and now looking towards digitally fabricated homes. This tiny component, or its strategic absence, tells a huge story about how we've always innovated, adapted, and pushed the boundaries of what's possible to put things together.
It really does.
It's truly remarkable to see such a grand narrative wrapped up in such a humble object.
Yeah.
We've just taken quite a vast journey, haven't we? All starting with a simple nail.
Or even before the nail.
Right. From ancient methods emphasizing complex wooden joinery or the very earliest, highly valued metal elements, through the meticulous craft uses of iron pins and simple hand-forged nails, right up to the modern standardized fasteners that enabled a boom in wood frame construction and continue to evolve with visions of digital fabrication.
What this deep dive truly emphasizes, I think, is the unseen genius behind even the most ubiquitous and overlooked components, like the nail.
Unseen genius, I like that.
These aren't just simple objects. They are profound products of centuries of human innovation, deep metallurgical knowledge, and constantly evolving construction needs and economic pressures. Their story is a testament to how fundamental challenges like how do you effectively and efficiently connect two pieces of material have spurred continuous technological advancement.
Subtly reshaping our world, one fastener at a time.
Exactly, without most of us ever noticing.
So the next time you see a nail, maybe sticking out of an old piece of wood, or maybe you're hammering one in yourself, or any ordinary fastener holding something together in your world, perhaps you'll think about the incredible journey it took to get there.
Yeah.
You might consider the countless hands, the brilliant minds, the industrial innovations over centuries that shaped its existence, making it a silent, yet absolutely indispensable part of our daily lives.
Makes you wonder, doesn't it? This raises an important question for all of us. What other invisible components are shaping our world right now, quietly enabling grand narratives of technological change that we're barely aware of?
Like what? What else might be out there?
Well, perhaps the silver screw, which has its own fascinating history. Or the ubiquitous bolt. Or maybe even the advanced adhesives holding modern cars and airplanes together, materials science operating at a chemical level. What untold stories will they tell a century from now?
That's a truly thought-provoking question to leave us with. What are the nails of the 21st century that we're overlooking right now?
Something to ponder.
Definitely. We encourage you, our listeners, to keep an eye out for these hidden histories, sparking your own curiosity about the everyday marvels around us. Thanks for joining us on this deep dive.